Hey, it's me again. AP test is coming up soon, so I'm going to put some more content out for you. This is a pretty common question type for AP Calculus. It's got tabular data, just meaning data presented in a table for you. This is number 4 on the 2018 AP Calculus exam. Both AB and BC have this as their question number 4. So let's take a look at it. The height of a tree at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table above. All right. Part A says use the data in the table to estimate h prime of 6. Using correct units, interpret the meaning of h prime of 6 in the context of the problem. So let's go to the whiteboard. I've copied the table here for our convenience. We want an approximation of h prime of 6, which is the rate of change of h when t is equal to 6. We don't have t exactly at 6, unfortunately, but we have t at 5 and we have t at 7. So what I can do is I can say that the rate of change of the function h, right, that's the derivative. Derivative is the rate of change. The rate of change at 6 is approximately the average rate of change when t goes from 5 to 7. So I'll use a little squiggle for approximately. And remember, the average rate of change is just delta h over delta t. Right? This is from physics, your average rate of change formula. Right, so dh dt when t goes from 5 to 7, which is h of 7 minus h of 5 over 7 minus 5. And I have these values, which is why I chose 7 and 5, right? H of 7 is 11, h of 5 is 6, so that's 11 minus 6 over 7 minus 5. 11 minus 6 over 2, which is 2.5, looks like. And it also wants the units. So since h is in meters, the change in h is also in meters. And since t is in years, the change in t is also in years. So the rate of change is just meters per year. .5 meters per year. So here's an interpretation. The h prime of 6 represents the rate of change in the tree's height when the tree is 6 years old. And it asks you to give that interpretation in context, so you better have the word tree in there somewhere. And you better have years probably as well. And if you just said h prime of 6 represents how fast the tree is growing when it's 6 years old, that would also get credit. Same meaning. Let's look at part B now. Explain why there must be at least one time t for 2 less than t less than 10 such that h prime of t equals 2. This is one of those questions about existence of a point on an interval, and it's all the different value theorems, the extreme value theorem, the intermediate value theorem, and the mean value theorem. Probably the most important of which is the mean value theorem, which is the one that's going to happen here, because it's asking to show that there's a point where the derivative of our function has a certain value. So let's recall the mean value theorem. Mean value theorem says the following. For a function, we'll call it h, since that's what we're working with. For a function h, which is continuous on the closed interval AB and differentiable on the open interval AB, there exists some point inside that interval, strictly inside. A less than t less than b, let's actually call it a less than c less than b, with h prime of c being equal to the average rate of change, once again, h of b minus h of a over b minus a. The instantaneous rate at this point c is equal to the average rate of change, which has this formula here. H of b minus, so the h evaluated at the two endpoints divided by the distance between the two endpoints. So that's the general statement of the mean value theorem. And if you know that, then all you'd have to write on this question is that the following. Let's take a moment to behold that theorem. Now I'm going to erase it. All you got to write is something like this. By the mean value theorem, and I'll add, since h is twice differentiable, which guarantees that it is both differentiable and continuous on this interval. Since h is twice differentiable, there exists a point c in the open interval from 2 to 10 with, well, I'll call it t. There exists a t with h prime of t equaling h of 10 minus h of 2 divided by 10 minus 2. What is h of 10? 15. H of 2 is 1.5. So 15 minus 1.5 over 10 minus 2 is 8. And we get, hold on, this seems incorrect. Minus 1. Oh boy. Here I have led you down the garden path, haven't I? So it looks like to me we're going to have to pick some different endpoints to make sure that we get it equal to 2, because this won't be equal to 2 exactly, right? This is 13.5 over 8, which is not equal to 2 like we wanted. Whoops. But we do have more endpoints, or more points within this interval that we can check. I just got to make sure that the distance, that h of this minus h of that over this minus that is exactly 2. So let's try again, right? Instead of 10 and 2, we'll have to try something else. But I think 3 and 5 is going to work. So let's change 2 and 10 to 3 and 5. Certainly if there's a point between 3 and 5, it's also between 2 and 10. So between 3 and 5, we've got h of 5 minus h of 3 over 5 minus 3, which is 6 minus 2 over 5 minus 3. That's 4 over 2 equals 2. And that does it for part B. That was a tricky one. You had to look at a sub-interval of the entire interval to solve that part. All right, part C says use a trapezoidal sum with the 4 subintervals indicated by the data in the table to approximate the average height of the tree over the time interval 2 less than or equal to t less than or equal to 10. So the average value of a function, in this case the average value of the height, average of the height, is just 1 over b minus a times the integral from a to b, the definite integral along that interval of the function. So we want an approximation for this based on the trapezoidal rule. Now, what I always got to do when I find these approximation, Riemann sum, or left endpoint, right endpoint approximations, trapezoidal rule, midpoint rule, is I try to draw a little picture. If I'm doing this by hand, especially, I don't try to remember those formulas that have weird, different coefficients going up and down. I just draw the picture and let that be my guide. So here is the picture. All right, there's my 5 data points that I've plotted on a t-axis and an h of t vertical axis. The trapezoidal rule means that I'm going to draw little trapezoids whose bases are down on the horizontal axis. This is 7. This one is 10. And they're trapezoids, so there's a slanty edge at the top. The parallel sides are vertical to each other, right? The parallel sides vertical, and then we've got this. So I'm approximating the definite integral, which is the area under this curve. I'm approximating it by using these trapezoidal shapes. And now I just need to do a little bit of basic geometry to figure out what is the area of each of these trapezoids. In general, the area of a trapezoid, of course, is 1/2 times the height times base 1 plus base 2, right? In this case, the bases, which are the 2 parallel sides, are vertical, so I'll just label each base with its own height. This is 1.5. Sorry for the small writing here. 1.5. The next one is a height of 2. This is a height of 6. This is a height of 11. And this is a height of 15. Those are the bases, respectively. And then the heights are, confusingly, the horizontal distances here. So the height here is this distance, which is 1. This one is 2. This is 2. And this one is 3. So what I'm finding is that the integral from 2 to 10 of h of t dt is approximately, according to that trapezoidal rule, 1/2 times the height of the first trapezoid, which is 1, times 1.5 plus 2, plus 1/2 times the height of the second trapezoid, which is this 2 here, times 2 plus 6, plus 1/2 times 2 times 6 plus 11, plus 1/2 times 3 times 11 plus 15. That's not the average value of the height of the tree, though. That's the definite integral. The average value of the height, you have to multiply by 1 over b minus a. So I need to have in front of this a 1 over 10 minus 2, or 1/8. And so I better just add an approximately 1/8 times this entire expression here. And because this is the AP Calculus exam, I am done evaluating this expression because I do not have to simplify my answer. This will get full credit on the AP Calculus exam. And if you simplify it to a single number, as you are so inclined to do from your years of schooling, and you make an arithmetic mistake in there, you might not get full credit. Okay, so I'm going to stop right there on this part and move to part D. The height of the tree in meters can also be modeled by the function g, where g of x equals 100x over 1 plus x, where x is the diameter of the base of the tree. When the tree is 50 meters tall, the diameter of the base is increasing at a rate of 0.03 meters per year. According to this model, what is the rate of change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall. Okay. So let's start with what it is asking for, which I just read. What is the rate of change of the height with respect to time when the tree is 50 meters tall? So I'm going to write some stuff on the whiteboard now. So I've given the equation here, and I reread the question. G is another word for the height. So h was the height before. It was with respect to time t. G is now the height with respect to this new variable x. That is the diameter of the base of the tree. So that's what we're working with. And it wants to know, once again, what is the rate of change of the height with respect to time? So we want, this is one of these related rate questions, right? We want the rate of change of the height with respect to time. dg dt. Right, we're done with h. We're working with g now. G is the height. The rate of change of the height with respect to time at the time when the tree is 50 meters tall. So at the time when g equals 50, that's what we can write. So that's what we're looking for. And now we need to focus on the information that's given to us. Let me go back to the question. What it tells us in that second sentence is when the tree is 50 meters tall, the diameter of the base is increasing at a rate of 0.03 meters per year. Okay, let's try to write that down. The diameter of the base is increasing at a rate. So the rate of change of the diameter of the base. That's the rate of change of x. X is the diameter of the base. So dx dt, the rate of change of it's increasing at, so dx dt, and it said when the tree is 50 meters tall. So that's, again, when g is 50. When g is 50, the rate of change of x, the diameter of the base, with respect to time, is 0.03 meters per year. So this is what's given to us. Now we can start thinking of this as a basic related rate situation, right? We want dg dt, we've got dx dt. The relationship between them is that, well, not related rates, but a chain rule, right? We have the thing that we want, dg dt, should be equal to dg dx multiplied by dx dt. A nice way of writing this chain rule using Leibniz notation. dg dt equals dg dx dx dt. And this is the thing we want. This is right here on the left. dx dt is the thing that's given to us right here. And then the only question is, what is dg dx when g is 50? That's the derivative of g with respect to x. Well, okay, we're given g of x. I guess we need to take the derivative of it, right? So let's pause for a second. All right, on the top right corner of the board for you now, I have taken the derivative of g with respect to x. Here's the original function, g of x equals 100x over 1 plus x. That is a quotient rule situation, so I took low d high less high d low all over low low, multiplied things out, cancel things, simplifies to be this expression here. And what I'd like to know is, what is the value of this expression when the height of the tree is 50? Uh-oh. X is not the height of the tree. I can't just plug in 50 for x. This is a tricky one. G is the height of the tree. G is the height of the tree. So I need to figure out what is x when G is 50. And then I can plug that value in for this x to get dg dx when G is 50. Let's do it. So, when g is 50, when g of x is 50, we'll get 50 equals 100x over 1 plus x, multiplied through by 1 plus x, 50 plus 50x equals 100x. 100x minus 50x is 50x. So 50x equals 50, or x equals 1. All right. So when the tree is 50 meters tall, we're thinking that the base is a 1 meter diameter, so x equals 1. So let's plug that in for g prime of x. So I'm going to erase. I'm running out of room. I'm going to erase what I just wrote. Remember, x equals 1. And now it's gone. And if I plug in g prime of 1, using this formula, it's going to be 100 over 1 plus 1 quantity squared. It's 100 over 4, which is 25. So that means that this thing here is dg dx was 25, so this is 25. And dx dt was 0.03. That was what we were given. So the answer is, I guess 25 times 3 is 75, so this is 0.75 meters per year. And that will be the answer on part D. Pretty tricky little problem for a calculus AB level problem. It's on both tests. There you go.